This is a short series of slides to assist paraglider and hang glider pilots in using Skew T meteorological graphs. In this section, we will look very briefly at what we can learn from using Skew T or soundings graphics as part of our flight planning, and we will also spend some time describing the faint background lines on a Skew T graph and how they can help us infer the key information that is likely to be of interest to us. As free flyers, we might use a Skew T on the day of our intended flight to get a better understanding of the likely strength of climbs, the height of any inversions or areas of possible turbulence, the degree and type of cloud cover, and tendency for spread out, and to assess any risk of overdevelopment and storms. When reviewing the week ahead, using the rest of our favourite weather and flight planning tools, we might generate a Skew T graphic to help us choose which weather forecast looks most convincing and to try and anticipate some of the likely features and characteristics of the incoming air mass. Specifically, the soundings data being collected around the world and in air that is heading our way can help us understand the stability of a future air mass and its propensity to support convective thermal development. Kelly Farina spends a lot of time talking about the various types of stability that might be a feature at different levels of the air above us. His series of videos are now tucked away behind a Patreon paywall, and they offer a great description of how air mass stability will impact on our day. We will see in the next part of this series how the lapse rate of the surrounding air can change with height and how that can influence the vertical velocity, acceleration and bumpiness of any rising bubble of air. Let's now take a little time to disentangle the graph and figure out what the various lines are telling us. At this stage, we should mention an exceptional British pilot and great free flight hero of both hang gliding and paragliding, Steve Ham. Steve now lives and guides in Piedrahita in central Spain, and he is an example of an experienced pilot who uses Skew T information to inform his flight planning on a daily basis. Steve Ham makes use of Skew T information that has been derived from RASP data, but which is then presented slightly differently by two Spanish pilots from a local paragliding school, Uri and Noel. If you visit the Fly Piedrahita webpage and navigate to Steve's weather section, then you can find several links to soundings and Skew Ts. The link includes a really helpful written description of how to interpret Skew T information. Some of that information is used and reproduced in the next few slides. There are 5 background lines that make up the basic Skew T graph onto which the soundings information can be plotted. The first basic set of lines are the ones that run horizontally across the graph, parallel to the x-axis. These mark certain isobars, or lines of the same atmospheric pressure, and they are also a proxy for height. For our purposes, we can think of 900 millibars, or hectopascals, as being equivalent to 1,000 meters or 3,000 feet, and 850 millibars as being equivalent to 5,000 feet. The second line is the one that gives the Skew T its name. They are the isotherm lines of equal temperature that travel from bottom left obliquely across upwards and towards the top right at an angle of around 30 degrees. We will see later on, when we describe our soundings information is collected, why we choose to skew these lines across at this oblique angle. The third set of lines mark the trajectory of air when the water within the air is still present as a gas. These lines mark the dry adiabatic lapse rate, and they describe a curving arc as they rise from the surface. The fourth set of lines describe another curving trajectory, and this time the lines illustrate how the air cools once any water within the air has condensed and formed cloud. we will recall that air cools less quickly as it rises when the water within it has reached the dew point and has condensed. This is the arc of the saturated adiabatic lapse rate. The final and fifth set of lines are another straight set of straight lines, and they are usually shown as dotted lines running from bottom left to top right at a slightly less steep angle as the isotherm lines. These lines illustrate how the dew point of the unsaturated air changes with height, and they are rather confusingly known as the saturation mixing ratio lines. This image is a summary of all our 5 background lines against which the data we collect can be plotted. They are the isobars in black, isotherms in red, dry adiabats in brown, the saturated adiabats in blue, and the saturation mixing ratio in green. It is against this background mesh of lines that meteorologists plot 2 temperature lines. They are the temperature of the air at different heights and the dew point of the air at that height. The radiosonde also records wind direction and strength and rain and cloud against height at the same time. In the next section of this series, we will look into the data points that have been plotted on our graph and what we can learn from it.